perovskite is in ferroelectric structural crystal structure, it is possible. And you're able to influence on properties using different kind of salt. It is also for piezoelectric materials. It is perovskite is very simple materials, very long mode, but do some achievements in, for example, in synthesis, in structure description, and improving of preparation technology, they obtain a new life. And it is perovskite, as you see, it is a typical multifunction materials. It possesses a huge different application among superconductivity, and it is amazing materials, but also many different structure may be using and should be investigate for improve our life quality. Yes, it is amazing when people are able to conjugate a big organic structure into perovskite structure. I think it was one of the best achievements in, I don't know, chemistry, material engineering, I don't know. And you have a question.
So in your last slide, you have shared one graph, pictorial graph, regarding the perovskite and tandem solar cell efficiency.
Yes.
It's about 33%. What's about the Shockley cohesion limit of this?
Yes, and yes, Shockley limit can be over when we make tandem elements, because it is some limitation regarding simple solar cells, because most such prediction regarding limitation, it was connected with a simple mechanism. But when we afraid, for example, improving internal reflection, and we make some specific interface between materials, we can over, but it is not from physical point of view, but it is from improving technology. And also, when we have tandem cell, all of them not over limit, but together give interesting results. It is interesting because most of models not include real behavior of materials. It may be idealized, because we not take account all parameters. Yes, and when you, for example, calculate frequency of balance, you take account that it is angle is very small. Yes, and it's many solution show, for example, utilizing simplified model, and in practice we can sometimes battle. We're not able over speed of light, but some theoretical prediction should be changed, because maybe we not take account all required parameters. We some lost do a problem with a solving equation, etc.
Then what's special about this perovskite regarding to this limit? Does this kind of cell can overcome this limit?
I think maybe I think no, but as I thought, when a special solution maybe help, because but it is a very sophisticated technology of preparing materials, and it is, for example, molecular strength between materials. We can improve some technical improvements which give us opportunity to improve such properties. But a second question is connected with economical sense, because one is science, one is a laboratory, one is a special application, for example, in space, or in military application, when we not take account economy. We need only properties, and for such special application, is difficult to find a money except government money. Yes, because for example, when you have opportunity to produce cheap solar cells with efficiency, I think 35, Samsung give you, or another manufacturer give you a huge money. But when you told I have a 50%, but it will be $2 million per square centimeter of solar cells, it will be maybe interesting. Maybe a space agency maybe give you, because maybe they interested. Because special material science is strongly connected with economy. It is huge money is from such sources, and I think that we should wait for next big progress, because I think that we are close a limit when maybe somebody discover new phenomena and new materials, because it is sometimes maybe not intentionally investigate some different properties. Okay, thank you.
So I'll divide my talk into two parts. So today I will try to explain the first part, and then tomorrow or day after tomorrow I'll try to take the second half. So after the completion of this particular lecture, so our students will take you to our department, where you will try to, they will try to give the demo about the preparation of nanomaterials with two different methods, and then we'll try to show you, as I mentioned earlier in the morning session, we'll try to show you the field emission scanning electron microscope. Right, we'll try to give the demo of FESEM. So that completes the today's session, and tomorrow, as usual, you know the schedule. So in the morning session, Professor Michael will deliver 3 lectures, and then he will have the tutorial in the afternoon. Actually, thought of taking today, but from the morning, right, 9:30 to 1:30, he had 4 lectures, right? So we have to respect his age also, right? So that's why I force him to take rest, right? He will continue tomorrow, right? So I will try to share my experience, what we are doing for last 20 plus years. So we are working on the glasses, the amorphous material. Similarly, you are working on the crystalline material for different types of application. Like we have started with the glasses for photoluminescence properties, glasses and glass ceramics for the biomedical application, especially the tissue engineering application, and then the other part, what I mentioned here about the crystalline material. So we are working on the crystalline material also, basically for the photoluminescence application, the nanopass parts, and then the second is related to the tissue engineering application, and then followed by the drug delivery, bioimaging, and then we are working simultaneously on the energy storage. I mean, what I'm talking about, the supercapacitors also we are working, and then recently we have started even the photocatalysis application. I mean, we are using this material for wastewater treatment. That's why I mean I kept the title as fabrication of amorphous and the crystalline materials for multifunctional application, which suits to our title of the GAN program. So in this talk, I won't go much about the photoluminescence application of the glasses. I will try to stress more on the biomedical application, right? Before going to discuss about the biomedical application, what are the material we are going to use? If you want to use a material as a biomaterial, what are the attributes, right? I will try to explain the fundamentals first, and then I will try to share the research findings, what our scholars are doing for last decade, one decade. So I have the results with respect to both amorphous as well as the crystalline material. Now, if you want to use any material as a biomaterial, so if you start from top to and if you end at the bottom, right, you can find different tissues in the human body, right? We'll have the hard tissues, we have the soft tissues, right? We have the hard tissues like bone, the teeth, and then soft tissues related to the eye, related to the ear, right? And so many other parts are there in the human body, right? So we can able to use partly or completely can replace it, or we can able to use as a filling material. We can able to develop the the synthetic organs by means of using this material. So if you want to use any material as a biomaterial, it should possess some attributes, right? It should have the biocompatibility, it should have the cytocompatibility, it should have some sort of mechanical properties also, because you are going to deal with soft tissues, you are going to deal with hard tissues. For example, you take bone, right? So if you want to replace any part of the bone or completely or partially, right? So the material should have some not only the biocompatibility, cytocompatibility, it should have the mechanical properties, because if you take this bone, this bone, this bone or this bone, it is a part of the body and it will try to carry the entire weight, right? So I may have 50 kg, 60 kg, 7 kg, right? Your bone should have the capability of carrying that particular weight. So that's why we are going to concentrate on the mechanical properties, like the mechanical strength, hardness, comparative strength, flexural strength, ductility, and so on and so forth. So which is very much essential to develop the hard tissues, right? This is regarding the mechanical properties. And then the machinability is also very, very important. You want to extrude it and you want to mold it and into different shapes. So the manufacturability, machinability, these are all the other properties along with the biological studies. And similarly, we are going to measure some of the physical properties, which I am going to discuss one by one, right? So whatever, it's not like you are keeping a book in a rack, right? So it is a material you are going to keep inside the human body, right? So your physiological system should accept your material, right? So if the material is toxic and you are keeping or using as a biomaterial, then it may harm your organ. As a result, the patient may die. So the toxicity is also very, very important, right? Then similarly, there are certain properties you are going to study as far as the metal is concerned, right? So it has to be inert material, or it has to be a bioactive material, or it has to be bioresorbable material, or so there are different classification, right? Different categories of material are there, which you are going to discuss one by one, right? So first of all, the material, whether it may be in the form of powder or rod, or in terms of a wire or a sheet, right? The body should accept physiologically, and it should interact with the body, and it should resorb and it should help the body part to grow. So these are 4 generations: first generation, second generation, third generation. So it is not new. So the biomaterial, they are started 50 years, 60 years, 70 years ago, and then there are a lot of developments. So if you see the first generation, the material are known as inert material. So there won't be any activity which is taking place between the metal and the tissue, just like mechanical interlocking. That's the first generation. Second generation is the activity is going to happen between the material and the physiological system, right? So there will be reaction, and then the material will try to participate in the reaction and help the tissue to grow, right? That is the second generation. The third generation, what people are talking about, is the resorbable material. So the material you are going to use as implant, right? It will be resorbed by the tissue, and it helps the tissue to grow. And similarly, nowadays people are talking about 3D printing with respect to the organs, right? That is also the present generation of biomaterial. So here there are wide variety of materials are available. So people have started with metals and their alloys like chromium, zirconium, chromium, molybdenum, right? So all these metals, they are exclusively they are working for the hard tissue applications, right? Like the bones, the skull, right? So these are related to the metallic implants. And later people have observed some difficulties with respect to these material because they are heavy weight. The metals, if you use as implant, right? So you know that metal is heavy weight. The first thing. Second thing is that there is a possibility of corrosion if you use a metallic implant in in a body, right? So it has to be there for few years. You won't replace every day. You won't replace every week. What you are going to do? You are going to implant the material and you'll keep it for few years. During the course of reaction, there is a possibility of what you call the corrosion. As a result, what happened? The tissue will try to damage. That is also difficulty, right? So like this, there are certain disadvantages with respect to the metallic implant. That's why people are more interest towards the ceramics than the polymers, because polymers are the lightweight material, right? And there are some degradable material, there are toxic material. So that is also one of the the problem people are facing with polymers also. Later they are interested towards the composite materials, right? So composite, as I mentioned in the last class also, right? So composite will have two parts. One is the matrix, other one is the reinforced material. So matrix can be metal, matrix can be ceramic, matrix can be carbon, matrix can be glass, and into which you are going to reinforce any material. It is in the form of a powder, can be in the form of fiber, right, in the form of a sheet. So we are going to have different category of composites: PMC, polymer matrix composite; MMC, metallic matrix composite; then CMC, ceramic metallic composite, or carbon matrix, or nowadays people are talking about the hybrid material. So I am not going to discuss about the other properties, other applications of composite. So here I am going to concentrate more on the biological aspect rather than the other, the mechanical application. Usually the mechanical people, they are going to use in the automotive industry, and then even for the defense application. So that is not my area of discussion. My area of discussion is related to the biological aspect, right? So here so these are some of the biomaterials. So you can see here. So there are these are different generation. So when you started our research journey in biomaterial, it was 4 categories, 4 generation. Now it was reduced, it made into 3, right? The first generation implants, you can see most of them the metallic implants, right? And then the second generation is the bioactive and then bioresorbable. We are working in the second generation, and then even we have started to work even in the third generation also, right? But it will try to take some time, right? Here you can try to see the ceramics scaffold, the microspheres, then the fiber, the scaffolds. So this is the latest material which people are working. and this so this already explained to you, right? So a part of the body which has lost the function, you can replace it, or you can able to replace completely, or you can able to correct the abnormalities in the spinal cord. That is also happened by means of the biomaterial. And then for example, you take the pacemaker or the stent, which will try to improve the function of the heart, right? And similarly, you can able to assist the healing procedure, right? So for example, you take the structural, pharmaceutical, you know about the sutures, right? Once the operation is performed, right, after cutting, right, they will try to stitch with the thread, right? So that is also one type of biomaterial. People are using the polymer based material, right? So that comes under the category of sutures. See, we know about the capsule, right? So which will have the medicine inside, the powder inside. So that capsule is also made up of a polymer which carry the medicine into the human body. That is also help the it will try to assist the healing of the tissue, right? So as I mentioned earlier, right, so it is reliable, economic, and then the first and foremost the important thing that it should physiologically accepted by the tissue. Otherwise, what happens, you cannot use it, right? It may be metal, it may be ceramic or polymer or composite, what it may be. The tissue should accept physiologically, then only you can able to use as an implant into the human body, right? So it can be natural, it can be synthetic, right? So it treats, replace, or it assists healing, it will try to improve the function of the body, right? So these are the different organs, and these are the examples of the material which you are going to use. For example, you take the artificial valve, artificial heart, and then the pacemaker. So these are some of the synthetic grown material. So usually this artificial valve, people are use ceramics, the DRDO, they use the artificial valves, they use ceramic material to develop those artificial valves. And if you see the second one, the contact lens or the intraocular lenses, people are using glasses, and then even the polymer, the plastics, either the ocular lens or the contact lens, right? And then regarding the ear, so these are the soft tissues. So if you see this ear, so these are the cochlear implant, right? The nose, the soft nose in the ear. So those comes under the category of soft tissues. So most of the time people are using the polymers and then composite to develop the soft tissues related to ear and then eye. And the fourth one is bone. As I mentioned earlier, this is hard tissue in the entire human body, right? You can start from the top, the skull, to the bottom, right? The bones, right? So the hip joints, the spinal cord, so all comes under this hard tissue. Similarly, having the muscles also, the artificial muscles also people are developing, the artificial skin also, the synthetic skin also, a lot of people are working. So these are the examples. And as I mentioned earlier, so if you want to use any material as a biomaterial, you should have these attributes, right? First one is the biocompatibility. So it should be non-cancerogenic, it should not lead for the cancer, right? It should not be non-pyrogenic, non-toxic, non-allergic. It should be compatible with blood, because you are going to implant this particular material as implant into the human body. And then the sterilizability, and then the physical property just now I mentioned, right, as far as the hard tissue is concerned. And then we have the other one, the moldable, extrudable. It depends, right, what of the tissue you are going to develop, right? So as I mentioned, there are wide variety like metals, ceramics, polymers, and then the composites also. So this is regarding the synthetic biomaterial. So polymers we can able to use for the ocular implants related to eye. Then we can able to use to develop the synthetic the skin, right? And then we can able to use as a drug delivery. The example is the capsule, right, which is to carry the medicine into the human body, right? And then the metallic implants, right? So we can use the screws fix as far as the bones are concerned, and similarly the dental implants, right? If you have visited a dentist, right? They used to have the caps, they used to have the filling material, right? So and they use pure ceramic, right? And if you are rich enough, you can have gold teeth also, right? It depends on how much you can able to afford, right? You can have the implants, and almost all the similar properties you are going to achieve with respect to the ceramics. The problem with the metals is corrosion and the heavy weight. So that's why people are more interested towards the ceramics. They are not corrode, they are lightweight, but we can able to achieve the properties similar to that of your metals. That's why it is expensive, but it is advantage compared to the metals. And the other category of metal is the composites. Even people are using semiconductor materials also to develop the implant microelectrodes. Even they are using as a sensors also, right? So these are some of the examples I mentioned. These are the advantages. These are, you can see here. So in metals we are having titanium and it alloys, cobalt, chromium we are having and their alloys, then the gold, silver, stainless steel. So all these material, zirconium is already there. So tantalum, titanium, so many alloys, different combination of alloys you are using, right? Basing upon the compatibility of the material. Similarly, you can see the ceramics also, and you can see the composites, some of the examples of composites, and then polymers. So this is the human body, right, from top to bottom, right, where you can able to find soft tissues, hard tissues, right, occlulences, the cranial, and then the ear related implants, dental related implants, the blood vessels, right. So the ligaments, the bone fixations. So they are given wide variety of material. This is the old picture, the old image, but now if you search in the net, you can find still more material, right. Not this, right. You will try to find semiconductor, you can find different types of sensor material also, along with these hard and soft tissues. But only important thing is we need to check the toxicity of the material, whether the material is toxic or not, allergenic or not, pyrogenic or not, cancerogenic or not. This is related to the biology, right. So we have a collaboration with the University of Hyderabad, and then the other institutes where they are having the biological, the cell cultures studies, facilities. So in collaboration with that only we are trying to do, and then we are having collaboration with mechanical department also, because this is not exclusively related to physics. This is a interdisciplinary area where the biology, the biotechnology, mechanical, physics, and all the areas you need to work out. So that's why we are trying to get some good results. So these are some of the implants, the hip replacements, right. We can find most of them are the metals, and that is the X-ray, right. After putting the implant, right, you can see the metal, the ceramic, and then the plastic liner. All three you can able to see here, and then the metal stem you can see here, and the ceramic ball you can see there. So these are related to the soft tissues, hard tissues, the bone, and this is related to dental, right. The cap, filling material, or you know about the root canal treatment also, right. So we can able to use even filling material also we can able to use, and the entire teeth we can able to replace with complete pure ceramic material, or on a metal people used to coat some ceramic. It depends upon how much you can able to spend or how much you can able to afford, right. So these are a different generation of you can see the first generation, you can see the different structure, different shapes of the bioactive or resorbable material. They will be in the form of cylinder, pellet, rod, and the third generation you can able to see the mesoporous material, the template, right. We can can able to develop by means of the 3D printing. But there are certain practical difficulties. If you overcome the practical difficulties, you can able to produce more implants. So this is regarding the activity. I don't want to go in detail, but so this is the protocol usually people used to follow. I mean, I'm talking about the people who are working in the area of biomaterials. This is the protocol they used to follow, and these are the tests they are going to do. Now, the first one, what you are doing is the first one. So, selection of the material, composition selection, making the metal either amorphous metal or the crystalline material, right. So, am I audible? Last. So, whether you are making glass, a glass ceramic or nanomaterial or crystalline material, right. So, you need to adopt the technique. If it is a glass, you need to make use of the melt quenching technique, or sol gel technique also you can able to use. If you want crystalline metal, you can able to use solid state reaction, you can use sol gel, you can able to use hydrothermal, you can use co-precipitation. So many methods are there. So first you need to prepare the material, right, and then you need to do the characterization, right. So you made a material. So anybody ready to make use of the metal and make it as an implant and allow us to put as an implant in the human body. I made a material, will you allow me to put into body, right. So we should have an environment similar to that of the human body, right. So which is nothing but SBF, the stimulated body fluid, which resembles the plasma, the blood plasma, right. So you have the blood plasma, there is the composition, and there is a protocol to make that SBF. I will try to show later. So SBF is similar to the blood plasma, right. So we are going to test the material initially with the blood plasma, so which is known as in vitro studies, means outside the human body. So first we need to test whether the material is active or not. So how you are going to test? Who is going to test? You are not ready to test. You are not sacrifice, right. So I need to create an environment similar to that of human body, then I need to test it. So you are going to test it, but how you are going to confirm whether your material is active or not? So for that we are going to do some characterization studies, what we physics or material scientists will try to do. We are going to confirm by means of XRD, by FTR, by FPSCM, by ICP, right. There are so many wide variety of techniques are there. By means of that you are going to test whether the material is active or not. That is the first thing, right. Next one is after developing the material you are going to do the mechanical properties also, right. Then so in vitro is over, but we need to check whether the material is toxic or not, because even if you find material is active, still you are not ready to accept my material, because you are worried whether it is toxic or not. Then what you are going to do? We are going to take the help of the biotechnology or biochemistry or microbiology. I am talking about the biomedical area people. People are working in the biosciences. We are to take the help of those guys, because they will have the cell culture studies. In cell culture, we are going to do all those studies which I mentioned: cancerogenic, whether the material is toxic or not, whether the material is allergic or not. So all these tests you are going to perform, right. So if you want to test whether the material is toxic or not, right. So we need to extract the salines from the human body. So what we are going to do? We are going to procure. We are not going to extract the salines from the human body. Nobody will have. We are going to procure, right, the salines, right. Bovine salines you are going to take, bone salines you are going to take, the sarcoma salines you are going to extract. We are going to feed those salines to the material, and you are going to leave like that for 24 hours and for 48 hours, and you are going to see how many cells are live, how many cells are dead. According to ISO standard, if the cell viability is above 70%, so about 100 cells you are feed, right, after 24 or 48 hours, if 70 or 80 are remaining alive, then you can say that the material is non-toxic in nature. After 48 hours, if you observe that there are only 20 cells, means the material is toxic, you cannot use, you have to throw it. So that test you are going to do it. So it is the cytocompatibility study or cytotoxicity study. Similarly, you are going to check whether the material is allergic or not, because that is also very important. So there are so many types of antimicrobials are there. So there are 50 to 60 are there. We are going to test what basing upon the availability, right? Like E. coli, SRS. With the help of that, we are going to check whether the material is allergic or not. Similarly, you are going to check the pyrogenic, other tests you are going to do it. So once you confirm after performing these two, if you confirm that the metal is active, bioactive, and then metal is non-toxic, non-cancerogenic, non-allergic, right? If you confirm these things, right? So that is our part. But people are not ready, because we cannot, take the implant into the body directly. We have to go for the step 3. Step 3 is very, very important. For last 14 years, I am trying for this, right? So we are, still we didn't get it. Maybe in my future. So we have started with Rajkumar, the first student. Even our Sushil also we are trying, but till now we didn't get, because it is very difficult. We need to spend 1.5 lakh rupee for particular sample to test the sample. I'm talking about the cost, because this is the rabbit modeling, the mouse modeling. Right? They used to develop, right, this type of a laboratory there. They are having the mouse, so not the mouse which you used to find in your home, right? It's a separate laboratory. So maintenance is very, very important, right? So they will try to cut the part where you need to replace it. Suppose you want to use your metal as a, what you call the heart tissue, for example, bone. Which part of the bone you want to replace it? So we need to approach the orthopedician, right? We need to approach the anesthesia guy, right? And we need to approach this, right? And if everybody agrees, then we need to cut and then replace our material, and then you need to check it out after 24 hours, 48 hours, or 1 week. Then we need to check it out with doing some characteristic studies. If you succeed, right, then you can go for the next study. So that is nothing but your in vivo. In vivo means inside the body, not human body, right? It is related to the mouse or related to a rabbit. So what we are having, not here in Hyderabad. So the they are having the mouse modeling, right? With mouse they are going to do it. So this is in vivo. So we are going to do in vitro, means we are going to create environment similar to that of the human body, in the laboratory, and we are doing the studies. That facility is there in our lab. We are trying to do that. So this is the third step, right? And once you succeed, then it will go for the clinical trials, right? So I think you might have seen so many movies, right? So recent movies, there is a drug mafia is going to happen, right? So it is not that much. Even to get the permission for third step, right, we need to follow a lot of protocol, and you imagine about the clinical trials, right? So clinical trials is a very, very difficult thing. I think it may not be possible throughout my lifetime. Okay, so that is the fourth step, and once you succeed in the clinical trials also, then your product will release right into the market. And but in if it is a general thing, it will try to take years together. But during COVID, right, you know about the vaccine, right? What is that vaccine? Bharat Biotech they have given, and one more, Covaxin, COVID, right? So because of the emergency, right, it took almost 6 months to 8 months, because the emergency, even for small vaccination or medicine, right, it will try to take. So they will follow these protocols. This is must, right? So this is the brief review of the steps which are involved. The material into product. So these are the steps which are involved as far as the biomaterial is concerned, right? So these are the some of the material. So we are doing for last several years, right? Mr. Sushil Rajkumar and one more guy, they work in the glass and glass material, and one Srinath and the one more student, they work on the this crystalline material, right? So it's going on. So our journey is going on. But for us, the inspiration is Professor Hench, right? So that is the base composition, right? For to start our work. So these are the material already I have given. So this gentleman has inspired us to work in this particular area. I think almost all 15 years back. I think if I remember right, Rajkumar se pehle. So almost all 10 to 12 years back, we have started to work this particular area. So this is triangle. So I'll try to show some of the results. I won't go in detail because for the completeness I am giving. But as far as our topic is concerned, we need to go more towards the biological aspect little bit, and then the remaining more, right? So usually when you are working with this biomaterial, composition is important, right? Glass composition is important, right? So in the composition, we need to understand the role of each and everything. So here if you see the composition, right, we'll have the glass formats B2O3 SiO2, they are the unconditional glass format, they will try to form glass, and then basing upon the type of tissue, right, we are going to use the dopant or additive, right. So we have chosen zirconium in this composition because of its mechanical properties, right, the fracture toughness, the yield strength, right, it is about 6 CGPA, that's why we are trying to GPA, gigapascal, that's why I have chosen this particular material, and it is excellent biocompatible material, right. So we will try to weigh the material, individually try to grind it with help of a motor and piston, right. After making a fine powder, we will collect in a crucible, the platinum crucible, we will keep it inside the furnace, we will heat it, and then by melt quenching technique we are going to make it the glass. Basing upon our requirement, the mold, there are different molds are available, we can make a pellet, we can make a rectangular shape, square shape or cylindrical shape, whatever the size, shape of the specimen required for the properties we are going to do. There are certain standards. If you want to do the mechanical properties, right, there are such standards, right. So accordingly we are going to make the sample. For example, if you want to measure the hardness, right, and then the mechanical strength, the other mechanical properties, there are certain dimensions. We need to prepare the sample accordingly. And you can make the pellet or you can make the powder for the in vitro measurements. So these are the characterization techniques you are going to use to confirm the bioactivity of the material, right. So these are the X-ray, XRD, Fourier transform, scanning electron microscope, EDS. Then for measuring the hardness, you are going to use the Vickers hardness tester, right. So the after preparing the sample by melt quenching or by any the chemical route, right, we are going to test whether the material is active or not. So the first step which is involved is in vitro, outside the human body. I mentioned about SBF. This is a very fast, low cost first step to check whether the metal is active or not, right. So if you see that table, right, there is a comparison between the blood plasma and then SBF. That SBF is almost all resembles your blood plasma. So those are the constituents of the SBF, right. So what you are going to do here, we are going to prepare the sample, make it a pellet, and then we are going to immerse the pellet into the SBF, stimulated body fluid, right. After 3 days or 7 days or 14 days or 24 days or 28 days, whatever the duration of time, we are going to remove the sample, right, and then we are going to check it out. We are going to characterize. Before immersion, we are going to characterize. After immersion, we are going to characterize. So why I am talking about this here? So we are testing whether the material is active or not. So how we are going to confirm means by means of this particular study. So what is going to happen here? So in the beaker, we can see the material. So that is SBF, and there is a bioceramic, there is a pellet. So there is exchange of ions between your SBF and the material and then SBF. So there is a exchange of ions. You know about the nucleation and then the growth. Heard about it in material science. So there are certain nucleation centers around which the material will try to grow and it will try to spread throughout the, or you know about the crystal growth, right? So here there are certain nucleation center around which the material try to start growing during your 3 days, 4 days, 7 days, 14 days, 28 days, whatever may be the duration. So what happened? You are immersing your pellet into the SBF, right? So what happened? There is an exchange of ions, right? So as a result, there will be change of pH, there is a change of degradation. All these are the tests to confirm whether the metal is active or not. So that's what you are doing here. So we are, checking whether the metal is active or not in terms of pH, in terms of degradation, or okay. This is about the biocompatibility, cytotoxicity, right? So this is a protocol we are going to follow to check whether the metal is toxic or not. So we are going to do in triplets. So this is 96 well plate. So each sample we are going to test in triplets, not a single, because we need to check multiple times, right? So accuracy is important, right? So that's why we are going to do in triplets, right? And we are going to test with the different materials with different concentration, right? So to each material we are going to feed around about 5,000 cells, right? And we are going to check by statistical analysis, we are going to check how much the viability of the cells, right? So this is regarding the toxicity here. Human astrosarcoma cell, so that is a bovine cell, human bovine cell. We are going to extract, and then those cells we are going to use to test whether the metal is toxic or not. So this is the biology. I don't want to go in detail. So this is regarding the mechanical properties. So we are going to measure the hardness, the fracture toughness, the compressive strength, the elastic moduli. Not only this, we are going to do the abrasion also, and similarly, we are going to do some the static analysis. Okay, so this is XRD for the amorphous material. So from this, you can confirm the metal is glass. It is amorphous in nature, right? Don't have any specific orientation, right? So this is confirmation whether the metal is amorphous or not. Now yeah, so this is before immersing the sample. So we have prepared the material, we have characterized the material simply, right? So we confirm that the metal is amorphous in nature, right? Then what you did, we immersed the sample in simulated body fluid, and we remove the sample after 5 days, and then we have characterized the sample. You can see the crystalline peaks, right, at 002, 211, 203. So these are the crystalline peaks. So this is related to the calcium phosphate, the hydroxyapatite. So what happened here? There is a leaching of ions between the metal and then SBF. So because of the leaching of ions, right, because of the nucleation centers and then the growth process, slowly as the time progresses, the layer has formed, and we are confirming by means of XRD. This is first step to confirm the metal is active or not. Similarly, after 15 days, we recorded the XRD. You can see the intensity of the peaks, it is increased compared to the previous case. Right. Similarly, with the FTIR, this is before immersion. We recorded the FTIR, and we saw some functional groups which confirms the presence of the metal what you have used. but after immersion, right, in simulated body fluid, and we are recorded after 5 days, we can see 560, 600, that peak is related to the hydroxyapatite. So we can confirm even from FTR also that the layer has deposited on the surface of the material. Not only that, with SEM also we can able to confirm. See here, this is before immersion, this is 5 days of immersion. You can see the white precipitates on the surface. After 15 days, we can see the cloudy lichen structure. So that is the layer which has deposited on the surface of the material. So that is the hydroxyapatite layer which is deposited. So which is confirm the metal is active. And similarly, you have measured the mechanical properties also. So zirconium is about 620, 600 to 620 range we are getting. I am talking about the hardness. So which is very good as far as the mechanical properties are concerned. So the hardness is 600 is not a small thing, right? So we can able to use for the hard tissues. That is the advantage of using, and this is to confirm whether the material is toxic or not. If you see, right, this bar graph, so Z0 is without zirconium, the base structure, the base material. Z1 is 1%, Z3 3%, Z5 is 5% of zirconium. And if you see the graphs, right, so all the bar graphs, right, they having the cell viability above 70% only, right. So the first one is the control, other 4 are with the different compositions, right. So all are slightly 80 and above 80. Second one is 70 and above 70. Third also 70 and above. Last one also 70 above. So as far as this particular bar graph is concerned, if you see here, we can observe that cell viability is above 70%. So as far as the standards are concerned, if the viability is above 70%, the metal is non-toxic in nature, right. So this is a cytocompatibility or cytotoxicity test we are going to do. Similarly, these are the optical images we are recorded. So you can see the flakes there, these flakes. These are live cells, the live cells, the bovine cells. We are going to feed the cells to the material. Those are the live cells. So we are having the 50 microgram per ml. Our material is 50 micrograms use, 2000 gram. So we can find the live cells, but there are little bit, we can see the dead cells also, but still it is above 70%, even 1000 micrograms, or means 1 milligram. So it is not toxic. So this is regarding the optical image. This is different ways of confirming the metal is toxic or not. So similarly, we did with titanium also. So see here, still you can observe the titanium dope is more biocompatible with the glass material. See the crystalline peaks. You can see the functional group corresponding to 560 and 561, 609 related to the calcium phosphate. So these are the, so not only that, you will have the confocal microscope also. These also will try to distinguish between the live and then the dead shells, right. So there are different ways, and you can see, you can confirm whether the metal is proliferating, we help the tissue to grow. That is also there. Not only active, sometimes what happens, the metal try to help the tissue to grow, right, which is nothing but the proliferation, right. So that also can able to confirm, you can able to see how the cell morphology is trying to affect with the material, because we are using our material. If it is toxic, what happened, the cell will try to die, right. If it is not toxic, right, is live, we can able to see, and we can able to see the proliferation also by means of confocal microscope. So many are there. So this is Sushil's work. So he has done some drug delivery studies also. Oh, right. So I'll try to take half an hour and then we'll go to the lab. So if any doubts, any queries regarding, you can ask. So the first topic, the first part what I discussed so far is related to amorphous material, the glass material. Similarly, you can able to use glass ceramics also, right? But the topic which I am going to discuss now, it is crystalline material, right? And here the material you can able to use for tissue engineering application, for light emitting application, right? The PASPAR application. We can use this material even for the supercapacitor application, like the energy storage devices, and then we can able to use this material even for the photocatalysis also. That's what our title, relevance of the title, right? So here we are not use the chemicals. As far as these studies are concerned, we didn't use chemicals. We concentrate more on the recycling waste, right? So we took the source, right? The rice husk, the eggshell, right? The peanut shell, the coconut hair, the baggage pitch. What I mean to say, we are use agriculture waste, we are use the food waste to start our work. Why you are use? Because these material, if you take a rice husk, or if you take the peanut shell or coconut hair or the baggage pitch, these are the major sources of silica. Silica, SiO2, not silicon, silica. And then we are use the eggshell, egg, the outer cover of egg. Snail also can able, the snail shell, you know, that is also we are use, and that is a source of calcium oxide, right? So our aim is to produce nano, crystalline material, right? So we took recycling waste material, we took the biomass material, and we have started I think almost all 7 years back, 7-8 years back, I started to work in this material. And why I use this material? Because the material are bioactive in nature, biocompatible, degrade, stability, they have the good mechanical properties. So there should be some reason behind selection of the material, right? So this is one area, and similarly we have chosen the industrial waste like fly ash, which is also the major source of silica. We have used GGBS, the granulated blast slag, which you are going to get from iron and then the iron ore industry. So these are the sources of silica and then calcium. So Pooja and then Gangadhar and then Veriswarup, so they are working on this combination of the material, but respective applications, right? Some of them they are working in energy storage application. Pooja, Gangadhar is working for multi-function application. Even Swarup also is concentrating more on the biological aspect, right? So here, we have started with something. We are working in something. It's it depends at that particular day what is your requirement, right? So even it depends upon how your research scholars will try to work, right? So it depends upon the ideas, right, which they are going to get, and then how effectively you are going to do your literature. That is also very, very important, right? So it's combination of, I can say, the permutation combination, what it may be. So our aim is to use these biomass, the recycling waste, waste to wealth. That is our motto, right? So these sources we are used, and then we have So this is our interest. If you see here, you can find major, I mean the calcium silicate constant, right. So these are calcium silicate based ceramic material, nanomaterial, right. So you can see wollastonite, dicalcium silicate to hadrostenite, malolite, all these are the material we can able to grow by means of using those recycling waste. Combination of agriculture waste, food waste, then industrial waste. With the help of them, we can able to, I mean, cover all these, structures. So those structures, they are having the multifunctional applications. So the beauty of those structures, they are having the perovskite structures, we can able to develop the sensors, we can develop the biomaterials, we can develop the energy storage devices. So many applications are there. That's why we are interested towards those material, right. So if you see here, as I mentioned, rice husk is the major source of silica, right. It contains almost 99% of silica, right. And then eggshell, it contains the calcium carbonate, right. If you heat it, make it powder, and if you heat it, what happens? It dissociates into calcium oxide plus carbon dioxide. So carbon dioxide will try to evaporate, will try to get CO. And then basing upon the selection of this material, 1:1, 1:2, or 1:3, we will try to get calcium silicate, dicalcium silicate, and tricalcium silicate, right. So selection is also very important. So this is the technique we are use to make calcium silicate by means of using the soil gel method. So we got the Indian patent for this particular method what we propose. So here these are the steps which are involved, right. So our students will try to give the demo for this particular method, the soil gel method, and then the hydrothermal method, preparing the calcium silicate or acarmonate structure, whatever structure we used to call, right. So here this is the method they are used to follow to prepare calcium silicate or zirconium doped calcium silicate, right. So we can get in terms of pellets, powder, or whatever shape we can able to get it. And then we have recorded the TGTTA for this sample, and from TGTTA we can confirm that the TC, the crystalline temperature of this sample, is around 778. So what we did, we have fixed the crystalline temperature of 800, then we anneal it. You know about anneal it, right? Annealing, you know, right? Quenching and annealing. Quenching means fast heating and then fast cooling. Anneal means with a prerequisite rate, you are going to slowly heat it and then slowly cool it. If you follow the quenching, what happened? It won't find sufficient time to find the brevis, lattice, or lattice sides to give a structure. Whereas if you follow the annealing, what happened? It finds sufficient time, right? So it results into crystal. Quenching results into glass amorphous material, right? So basing upon T and T, temperature and time, right? You will try to get the phase transformation from glass or what it may be, right? So we optimize the temperature, and then we anneal it for 2 hours, 3 hours, 4 hours. So time you optimize, temperature optimize, and as a result we got the structure. So this is the XRD, right, without immersion. Remember, the previous one is glass, we got the amorphous structure, but now it's a crystalline, it is having some structure. So we compare with the JCPDS data, it index, right, with that number, and the structure is beta wollastonite. So we are having different structure, anorthorite, wollastonite. I'm talking about the calcium, even in calcium silicate also, right. So this is the structure of the calcium silicate what you have prepared, and then we want to check whether the material is active or not. So what you did, we immerse once again in the SBF for 3 days, 7 days, 14 days, 21 days, 28 days, right. Then you have recorded the spectra. We recorded your XRD, right. So we can see a peak at 25 degrees, we can see peak at 31 degrees, right? So all those peaks are corresponding to hydroxyapatite, which means that the metal is active, which is trying to interacting with the tissue, right? I can say the SBF, right? Depositing a layer, right? So those peaks, right, corresponding to the hydroxyapatite. And see here, this is SCM. So the first one 0 days means without immersion. We prepared the sample, we recorded the SCM, we have the morphology. And after 3 days, 7 days, 14 days, we can see a precipitate which is forming because of the exchange of ions between the pellet and then SBF. You can see the thickness of the layer here. This is SBF layer thickness. This is a material, your pellet, and this is as the time grows, 10 days, what happened? The layer is thickness of layer is trying to increase. So the cross sectional I am trying to showing here. So it is the layer which is deposited on the surface of the material, right? Suppose this is a material, right? So you are immersing this material into the SBF. So because of the exchange of ions, right? So they will try to find the nucleation center around which the material try to grow, right? So the layer has deposited. So this is a microgram, the cross sectional view after soaking 3 and 7 days. So it is increasing from 49 micrometer to 120, 140, 150 micrometer. I am talking about thickness of layer. Means the metal is bioactive nature. So activity is more here, and you can see the EDS, right? The elemental analysis, right? You can see the EDS. So you can see their Ca to P ratio, right? Calcium to phosphate ratio, right? After immersion. So what is happening there? It is increasing 1.24, 1.56, 1.63 to 0.2. If you take the bone, right? So if you calculate the calcium to phosphate ratio of bone, it will be about 1.66. So you can see here it is almost all same as that of your bone. So that's why we can able to use this metal as a bone replacement. So similarly, you can confirm by means of FTIR. You can confirm the activity by activity even with pH also. See what is happening. So we are preparing the SBF at 7.4, but what is happening? It is increasing. So there is a change in the pH of SBF because of the material. Even degradation, the weight loss also can able to calculate. So why weight is losing? Because of the activity. So the same thing we are trying to confirm in different ways. Getting my point or not? Our aim is to check whether the metal is active or not. To confirm that, we are doing XRD, FTR, FESCM, pH, degradation, and so many things you are doing. So these are different ways of confirming. And then if you see this, so here the x-axis is the concentration of the material you are trying to use to check the toxicity of the material. 50 microgram to 1000 microgram per ml. Even you are used for 2000, 5000, even more than that also I use. Still we are finding that our metal is non-toxic in nature. See, the viability is near to 100%. So similarly, I measured the mechanical properties also, like the hardness and then the compressive strength. So similarly, we are doped with silver also. So silver we are using because it is having good antimicrobial properties. That's why we are trying to dope the silver also to calcium silicate. So this is the procedure you have followed, the soldier technique you followed to prepare the silver doped elastronite. So this is the XRD analysis, and you can see the growth of layer on the surface of the sample, right? You can see the different morphologies. So all these the recorded images with SCM. to confirm whether the material is active or not. So, on the surface of the material, the layer will try to grow, the hydroxyapatite layer will try to grow, and you can see with the time it is trying to change. So, it is having different morphologies, flake like structure, globe like structure, then you know about the cauliflower type of structures. So, we can try to see different morphologies as the. So, what actually is happening here, there is a leaching of ions between your material and then the SBF, right. So, because of that there will be nucleation centers around which the material try to grow, and with the time it will try to expand throughout the surface, and then the thickness of the layer also increasing, and it is spreading throughout the surface, which already shown in the previous image. So, similarly you can confirm by means of variation in the pH value, weight loss also, and this is the important test people are used to perform to check whether the material is allergic or not. So, we are going to do the antimicrobial study, right, and they are done only with 2 species, one is E. coli and then SRS. Not only these 2, we are having 60 to 64 species are there. It depends, right. Sometime you know about the skin allergies, right. Before going to use any ointment, you are going to check it here whether it is allergic or not. So, it is allergic to which species, that is also very important. So, basing upon the availability, right, we are done with E. coli and then SRS, and you can see it is you can see the images at the top, right. So, it is the inhibition zone, right. So, with the silver content, so the diameter of the inhibition zone is increasing, so which confirms that the material is antimicrobial. This is also one type of study you are going to do it. So, that is regarding in vitro cytocompatibility, right. And after this, I already mentioned about the in vivo studies inside the rabbit or mouse modeling, right, and then the clinical trials, and followed by the product release into the market, right. So, it is not that much simple as I mentioned, right. Up to the second stage or part of third stage, which I mentioned in the slide, is possible, right. But the animal modeling like rabbit modeling or the mouse modeling is a very difficult procedure, right. As I already mentioned in the beginning, I am trying for last 11 years, right, but I didn't succeed because we need to spend money is also important. For testing one material, we need to spend 1.5 lakh rupees, and even if you spend it, we don't have a guarantee that we will get the results, because maintenance of the environment, because the mouse is maybe 2 weeks, 3 weeks, 4 weeks. So, we need to cut the part. If you want to use as a bone implant, you need to cut the bone, which part of the bone, or whether at the joint or at the skull part or at the finger part. So, we need to check it out. So, for that we need to take the permission from the animal husbandry department, and then we need to consult with the orthopedician doctor, right. So, after testing the material, right, we need to record the X-ray, right, not this XRD which I am talking about, X-ray, right. So, that X-ray is I have shown. So, that X-ray is very important. So, during this course of the test, the mouse may die. That is also very difficult, because we tried but we didn't get the results. That is also a typical procedure which is which required to take a lot of permissions. So, once you succeed, then it will go to clinical trials, and then the last one the product will try to release into the market. So, this is regarding the first part, and in the next session I will try to explain about this thing. So, what we are doing now, and which is related to our GAN course, right. So, I will try to explain on the energy storage application, the optoelectronic application, and then finally I will try to show some light on the photocatalysis also, right, that in the next class. So, we will have a break now. After the break, I request to proceed to physics department, right. So there, I mean, our scholar will try to give the demo about those two methods. If time permits, today we will try to show you FECM. Otherwise, we will try to show you tomorrow or day after tomorrow, right? Because it is already 3:45, I think. Okay. So if you have any doubt, you can ask me or you can discuss right during tea time. Okay. Inhibition, yeah.
Can you explain what is that? That
Uh,
means it is
it won't. Yes. Otherwise, it is a measure of allergy.
in that zone those
That the micro it won't enter. That is because of the material. The material is inhibiting those particular, I mean, microorganisms. SBF. Which one? Yeah. You know the mechanism related to the crystal. Right? If you want to grow any crystal, right, there should be some inflation.
So it shows it is active.
It is helping to grow the crystal first. That is first. The second thing is related to when you immerse the material into the stimulates the body. Right? There will be exchange of ions. It requires some inflation. So silica or some other inflation. Around which
शाम को कुछ नहीं करना पड़ेगा शाम को हम आराम कर सकते हैं शाम के 6:30
and after the demo, so the tomorrow session I'll start once again at 9:30. So Professor Michael will try to deliver 3 lectures.